Cool, awesome. So yeah, everyone, welcome back. So today is Thursday, and what that means is tomorrow, you guys will tell me and Sam what is the situation and update with the teams that you guys are going to be forming for the capstone project. So today, the game plan is to take some baby steps and really trying to do a recap from what we've been talking about. Specifically, we talk about linear regression model, logistic regression model. We've done all that math, right? So now it's a time to, bring things down to Python and really make sure that not only is, everyone is able to use the code, but also, if I give you a new data, what you're supposed to do with it. So hopefully, today's session, I'm able to essentially walk you guys through both a regression problem and a classification problem using TensorFlow. And that's going to be the number one priority for today. Because the reason is tomorrow you guys are going to form teams. Immediately you're going to start tossing ideas. Then you need to have the code ready. Because if you have the data and you don't have the code ready, then you're like kind of, what are we talking about, right? People are going to get stuck. So I want to start with that. And then just on a high level, if you are following the slides, which is remember the 300-page lecture notes, right? If you're following that, right now we are chapter 4 and 5, so linear regression, logistic regression. We're gonna talk a little bit about cross-validation, sampling, bootstrap, but that's not going to take really a whole day. That's really some quick topics. So we're going to combine all of that with the tree-based model, because most tree-based model rely heavily on your understanding of sampling data and exactly what that means, and specifically what does that do to your final training performance. So we're gonna probably not today, maybe a little bit today, but we're gonna definitely talk about tree-based model tomorrow. Hopefully that will set you guys up on a relatively higher bar, and you guys have essentially linear regression, logistic regression, and decision tree random forest. Hopefully I give you guys all these algorithms, and that will be able to take care of a lot of like the entry-level data science projects. Pretty much you guys can pick whatever you want. So with that being said, let's get things started. First things first is we're gonna share screen, and I'm gonna do a live code walkthrough to show you guys exactly how these codes are produced and why do people code things this way. It's gonna be a Colab environment, so if you want to follow up, today is the day you follow up, because every other day I kind of use a template, and I kind of talk pretty fast through the code, so maybe you can't follow up. But today I'm going to type really slow. So if you want to follow up, today is the day. And then somebody else asked me a question earlier saying that maybe it's important, or maybe it's interesting to give out in-class quizzes or questions, or I think somebody else reflected the idea that they like the polling. So I'm going to try to do a little bit more of that. I think that's definitely a great idea to ask. Especially for a size like this is considered kind of like a small class, so hopefully everyone can be engaged as much as I can. All right, so with that being said, let me share my screen. All right, so can everyone see my screen? Give a thumb up if you can see my screen. Good, awesome, thank you. So right now I'm looking at the Google Drive. I am using the class notebook folder. But of course, for you, you can use whatever you want. You can be in your own Google Drive, anywhere, I don't really care, as long as you have a Python environment going. So first things first, I click on New, and then I click on More. Next thing is the Google Colab button. I click on that. Now, of course, create and share, and that will bring me here, right? So the name, I'm going to call Notes for July 21st, because that's today's date. So I'll say Notes for July 21st, 2022. Okay. All right, cool, awesome. So the game plan is this. I want to walk you guys through using live coding, use live data, how to upload data to how to produce results. So it's going to be from beginning to the end, the full spectrum. Okay, so first things first is you want to essentially load all the libraries. So we're going to import numpy as np. Numpy as np. Let me make it bigger. All right. Next, we're going to import pandas as pd. Import matplotlib.pyplot as plt. And then the last thing that's important that I forgot is OS. All right, okay, so first things first is we're gonna use data that exists here, right? So once again, the data exists in the sample data folder. It will always regenerate every time you have a new environment, right? You have a new collab, you fire it up, it's always there. But if you write some data there or you upload some data there, it won't be, unless you mount your Google Drive. Okay, so that I want to make sure that's really, really clear. But for in terms of the tutorial, I'm just going to use the data here just to save some time. So we're going to say load data, and first thing is to make sure I understand where I am in the directory. So here's one thing I want to show you guys, especially when you start coding. Okay, usually when I code, I type in specifically one small chunk of code, and I really make sure what that line is doing, and I understand what that line is doing is exactly what I want, and then I put them together. So when you guys go to my notebook, you're gonna see sometimes a long line. I don't really know how to write that off the bat, right? I did not know to do that in the beginning. I usually write the code out line by line, and then I put them together. Right, I'll show you. So first of all, I need to make sure I know where I am. So the first thing I do is list dir. And then maybe you hit Shift Enter to give you a new line, right? And you keep going, right? So this is okay, but you're gonna make your notebook very long. So the game plan for today is to, also show you guys how to write clean code. So first of all, you need to know where you are, and then you say, okay, sample data, that's what I want. Obviously, I want to go in there, so let me go there, sample underscore data. Aha, this is where I want, and all the data are there. JSON, MD, CSV, so on and so forth. Done. Now, what I'm going to do is I need to change dir, and then I need to list out the directory, double check, make sure I'm in there. Good. Now, what I'm going to do is I'm going to load up this training data. So I'm going to say, forget about training data. I'll just say California data. California. Oh, I can't spell today. California train. PD read CSV California housing train CSV. Obviously, add a quotation mark, right? This will be able to give you exactly that CSV file. So I do a quick sanity check .head, and this will give me oh, it's because I ran this already. Yeah. So this will give me this file. So then what's gonna happen is I'm gonna do the same thing for test set, right? Because I need both training and testing. So I do test, and then I say pd.read CSV California housing test CSV, and then I just do a quick sanity check of the dimension .shape test .shape. There. So that gives me the training set and test set. Right. So yeah, if you need to turn off your camera, that's completely fine, no problem. Yeah. So yeah. So as I was saying, we have training data and test data, and this essentially give you the subset of two subsets of data from the same source, but they're separate into two sets of data. One's training, one's testing. Obviously, the purpose is you train your model on one set of data so that you don't see the other one, and then when you test the other one, it's a fair comparison. So with that being said, I have all my data. Now I'm going to load up TensorFlow library. So I'm going to say import import TensorFlow as TF. This will give me TensorFlow library, and everything will be called a nickname TF. So I say build model. I can say linear model equals to tf.characters.models, and now I'm gonna start with sequential. And then I say linear model dot add. Here I'm gonna use the dense layers, right? So I'm gonna say tf dot characters dot layers dot dense. Make sure this is a capitalized, okay? Because this is case sensitive. If you do D, small cap D, no one knows what you mean. It has to be capitalized. And of course, it's a function, right? So you're gonna have to enter some arguments. First thing is units. Well, it's a linear regression, right? Linear regression. So we're not gonna have any hidden layer, not yet, right? We're just gonna enter 1 because that's all we want to produce. And then on top of that, we have activation function. I'm going to leave that alone for now because it's a linear regression model, so we're going to keep things simple. So I'll say comma, and then one thing I have not yet specified is the input shape. So there's going to be an input shape. And here I need to give the number of columns that I want my training features to have. So if I have 2 training features, then this is going to be bracket 2. If I want to have 3, then it's bracket 3, and so on and so forth. But here, I'm being a little bit loose because I have not yet defined what my training feature is. So let's do that. California housing train, which is here. That gives me all these things, right? So one thing I need to have is I need to define my target. Let's say it's a housing value. So median, quotation mark, median house value. So that's going to be my y. So that's going to be target. Here we can say define x and y. Now with that being said, I also need to define my x, right? So this is going to be California train, and I'm going to use the dot iLocation function to tell myself which part of the column I want to slice, right? So to make that a little bit easier to understand, let me comment out everything else. Let me just show you what the function does. So training data dot iLocation bracket colon means all the rows, because rows we don't want to slice, right? We want to slice the columns. So here, what do we have? 0, 1, 2, 3, 4, 5, 6, 7. So 7 is where I want to slice. So let's try that. 0 to 7. Oh, sorry, I have a typo here. It's a California train. My bad. All right, so now it's going to. I think I'm missing one, right? So households. Let's do 8. See if 7 is included. So no, that's medium income. That's fine. We want that in the features. So 7 now is included, right? If I do up to 7, 7 is excluded. If I do 8, then 7 is included, right? So a small trick about Python, the last number is always not included. If I do 9, then that will give me the target, right? It's the median housing value. So I don't want to do 9, I want to do 8. So this will give me all of the columns, and I'm going to give a name called X. So I'm going to put it here. Now I can uncomment these things. So to make my production line a little bit clearer, I'm going to call it X train and Y train, simply because this is training data. So with that being said, now I can do the same thing for test data, right? So Y test equal to California test median house value. And same with X test, that's going to be California test. Oops, there's no bracket yet. Dot iLocation bracket colon means I want all of the rows, comma 0 to 8. That means I want the first column all the way to specifically this column here called median income, and stop there. So if I run this, it will give me pretty much every component that we need to train our linear regression model. So let's run that. Great. Now, I always recommend students do a quick sanity check, right? You say display dimension. So you say x train dot shape, y train dot shape, x test dot shape, y test dot shape. So this is 17,000, and that better be 17,000, right? Because the length of your training data, they better be the same. Otherwise, you're missing a house that doesn't really have prices. That's going to be a problem. And same with these features, right? Here you see 8, and here on the test set, it better be 8. Because think about it, if you train a model with 8 features, and you go test set, you feed in 9 features, the model's not going to recognize what that 9th feature is, right? It has to be 8 and 8. So these are a couple of things for you to be aware of. If things go wrong downstream in the code, usually the recommendation is, okay, check your dimension first, because maybe something's wrong there. So with that being said, now we know, this is 8 and this is 8, and that means what? There are 8 features. So there are 8 explanatory variables in the model. So you say bracket 8. And that's it. So now you need to compile, right? So model.compile. First thing to do is what? There's a loss function, right? So we talk about all of that, mean square error, mean absolute error. And then later on, we're going to talk about cross entropy. But here, it's a regression problem, right? So we're going to say mean square error, MSE. And then there's also optimizer. So we're going to say optimizer. Optimizer. And we're going to say gradient descent. This S means stochastic gradient descent. So let's put some notes. MSE means mean square error. And SGD means stochastic gradient descent. So if you forgot what this is, right, remember that when we said in class, there's an optimization problem happening when you're trying to find the best solution, right? So it is an optimization problem. So what that means is you're gonna have to define a couple of steps. So first, define loss function. We use calligraphic L to represent loss function. Y is your ground truth, Y hat is your prediction. Second is you compute the gradient. So we talk about this Greek letter nabla, right? N-A-B-L-A, nabla. It's an upside down triangle. So nabla, what are you gonna do with nabla? Nabla is a partial derivative, right? So you do math cal, it's a calligraphic L, Y hat means the estimate or the prediction. So once you have these two things, now you can do your gradient descent, do your for loop, which is gradient descent. So how do you do that? Well, you say at each step S, update the weight according to the following. Okay, so what's the following? Let's write that out. Your weight, W, at the step S, okay, is updated by W from the previous step, S minus 1. Oops, I have a typo. It's S minus 1. And then subtract eta, that's a learning rate, times gradient. So recall the Greek letter nabla and loss function, calligraphic L. All right? So this gives you the gradient descent algorithm. And you continue the above until two things happen. Or maybe I should say either two things happen. Either two things happen. So what are the two things? A is you stop the algorithm yourself, right? You say, hey, this step S, I'm just going to do 10 times. That's it. So until S hits maximum threshold. Of course, the threshold is defined by the person, right? The data scientist. You know, if you don't like 10 to 20, if you don't like 20 to 50, and so on and so forth, right? Or the next thing is you can stop the algorithm when it converges, right? So, or until it converges. So what does this mean? This means that your error is going to a point that it's no longer decreasing. It's just flattened out. Or your accuracy flatten out, right? And we're gonna see what that look like today after I train this model. So what that means is accuracy or loss flattens out. So that means you're not learning any new information. You just keep training the model without any value going on there. So either this two condition is met, you can stop. All right, so with that being said, that's how you compile a model. And you run that code, you compile it. Oh, my bad, it's called linear model. Linear model, compile. All right, so last but not least, you just train the model, right? So recall what we did in class, that you always have to remember template, right? Recall machine learning template. So you always define your model and then train it. Train by using model.fit, right? So it's exactly the same thing. Model.fit. So model.fit is a function, right? You start training your algorithm, but you need to give the function something, right? You need to give the training data, validation data, test data, so on and so forth, right? So what do we have here? We have what? X train, Y train. Well, why don't we just use that? So here we say X train, Y train. But in order to really make sure everyone understands what's happening, I'm going to put my cursor up here, and let's see if it pops something out. Oh, my bad, it's a linear model. I keep forgetting that. Okay, so see the arguments of this .fit function has X, has Y, right? So I need to tell computer what these two things are. So to make things a little bit more clarified, I should say X equal to this thing. And same with here, Y equals to this thing, right? This way, people understand, okay, the X is really about the features, and the Y is about the target. So in other words, what is happening here is we learn a function, or sometimes you will call it a map. You can call it F, right? Such that F of X can produce Y with as little error as it can. And that's really what's happening, right? That's really what's happening. We're trying to find a function such that we throw the X in there, it gives us a Y, and that Y is good. That's it. That's all we're doing. So in this case, in my environment, I have X train, Y train. Of course, I feed in X train, Y train. For you, you can call it whatever you want. You can call it housing data, you can call it housing data train, you can call it first housing data, you call it whatever you want. It doesn't really matter to me. So, but you do need to have these things here in the argument, right? Otherwise, it doesn't know what you're doing. That being said, I think we still need to maybe a couple of more things. Let's see what else do we need. I want to make sure I have a validation data, validation split. Let me just correct myself. It's called a validation split, and it's going to be a fraction. Let's say 20%, right? So this is a fraction that takes 20% of the data randomly and perform on. And the reason it's called validation is because I need to come back up here and I need to criticize this model that I just created. Is it good? Is it bad? I don't know, right? I need to refer to some performance, some results. And that results cannot be training results. It needs to be some other results. But it can be the final test results, right? Because that is left in the very end. After all my tuning is finished, I perform one last round of tests on that. So if it's not training, if it's not testing, it has to be validated, right? So that's what's happening here. So I have this split here just to tell computer to do that. Now I think we're pretty much good to go. I can just specify epoch. I think I forgot how to. Is epoch or epochs? Epochs. So epochs equals to. I'll just do 10, so it's slightly faster. Oh, by the way, I need to make sure there's a comma here. So I don't know if you guys notice. If I don't have this comma, that's a bug, right? If it's a bug, then this will have a red line because it doesn't really recognize 0.2 epoch. That's not a thing, right? If I don't have a comma here, it'd be as if I'm typing 0.2 epoch. So the computer is gonna put those two things together. But that's not a thing, right? There's no such thing as 0.2 epoch. So that's why it has this red line down here. I'm not sure if you guys can see it. There's a red line down here. If you want to get rid of that, that's usually that's usually an indication of something's wrong, right? So what I do is I put my cursor here, I put a comma, then you wait a little bit, it should disappear. So there, it disappears. Okay. So this way I can start training my model. So I'm just going to go with it. You should be able to train. I don't know if it's accurate, right? And in this case, it's NaN. NaN means something's wrong. So what this means is you have your loss is blowing up, and it's blowing up so hard that you can't even write it down. That's what it means. So how I take care of the problem is I go back to my model and I need to rescale it. Okay, so let's try that. I'm just gonna take, let's see, what's the easiest way to do. So I'll say, well, it's a linear regression model. So I think the features, I'm gonna normalize it. But the price, I'm gonna rescale it. So that's what I'm gonna do. So features, which is your X, normalize. Target, which is your Y, rescale. Normalize does what? Normalize is basically saying X minus mu divided by your standard error, right? So it can't have negative numbers because it's calculating the distance between whatever data you are and the average. So of course, you can be less than average. That's what average means. Some are bigger than average, some are less than average. And then you rescale it by standard error. This tells you how many times of standard error that this X is compared to the average. Basically, what that means is you normalize your data. So scale is a completely different thing, right? Rescale is you take your X and you divide it by a maximum number of X. So if you do this, then everything will be between 0 and 1. So that makes your number smaller. If I don't do this, you're gonna see that I don't have any results here. The reason I don't have any results here is because my numbers are blowing up, right? Why is my number blowing up? Think about it. Let's take a look at the code. If you have your X train, forget about X train, let's say your Y train. These numbers are huge, right? Are huge. If you are making, even if you just add them together, it's a large number. It's not going to be a small number, right? It's going to be something like that. And now you're doing gradient descent on this, and you're having all of the training data together, and so on and so forth. Now you can imagine that this thing is gonna like blow up to scale, right? So that's gonna be an issue, and we need to take care of that, right? Otherwise, you don't have any results. So so let's try this. X train, I am going to normalize it. So what I'm gonna do is I'm gonna override it as X train minus X train mean, and then divided by X train. I believe it's STP. I forgot what that is. Let's see. X train dot mean. Right, that's the average. So how about standard deviation? Is that correct? Yeah, it's correct. All right, so awesome. That's correct. All right, so this line should be able to run, no problem. I'm doing the same thing with test set, right? X test equals X test minus X test dot mean, and rescale it with X test dot standard deviation, STD. All right, so now that's X. Now I'm gonna do the same thing for Y, but instead of normalize, I'm gonna rescale. So rescale is like this. If I take Y train and I plot it out, it's all these big numbers, right? Because the house is like $100,000, $200,000, a large number. So what's gonna happen is I'm gonna divide it by Y train dot max, because Y train dot max give me the maximum number in that vector. Right, so whatever that is, that's the largest number, right? So what I'm gonna do is I'm gonna divide that by all of my data. So now you can see it's like 0 point something, right? It's a smaller number. It's in between 0 and 1. And if you do that, then you can do a quick sanity check. If you do this max, it should be able to give you 1, right? Because if everything divided by the maximum number, which is the largest number, then the largest fraction is going to be 1 itself. Because you take the largest number divided by itself, that's going to be 1. So once that's clear, we're going to rewrite our Y train by saying Y train equals to something. And that something is Y train divided by Y train dot max. And I'm doing the same thing with test set. Y test dot max. So now, hopefully, after I do this, I get some numbers. Otherwise, probably something's wrong. So we're gonna run that. Of course, we're gonna recompile our model, right? Refit, and hopefully it gives us some number. So now it gives us some number. So at least it's learning something, right? It's not completely NaN, which is not a number, right? So it's learning something. So now you have a start, right? You have a pipeline. You have your code to load in the data. You have your code to build a model. You have your code to do the data processing. And then you have a code to train the model. So then you're done. Now, you need to be able to tell if this is good or not, good or bad, right? Like, what are we looking at? Is it good? Is it bad? We don't know, right? So we need to plot it out. So you say plot. And then earlier, we load in the PLT library, which is here, right? So all you gotta do is you can call PLT, which is a function. Sorry, let me correct myself. It's a library. And under that library, there are a bunch of other functions. So one thing about this is, if you just run it this way, you have not saved any of these results anywhere. You're just training it, and this will print out the statement of the training process. Okay, so this number 0.0527, 0.0271, none of these numbers are saved anywhere. All right, so that's a problem, right? So what we need to do is we need to save it as something. So history equal linear model.fit. This way, whatever that you're training will then be saved in history, right? So there's I actually rerun this twice without recompiling it. What that's going to do is it's actually going to start from the 11th epoch, not the first epoch, even though here it says the first epoch. And the reason is the memory carries over. So that's why earlier you see like 27 something, right? Now here it's like 226. So that's not supposed to happen. So what I'm going to do is I'm going to rerun the model. I'm going to recompile, and I'm going to retrain. This way, it will give you the training process from the beginning. Okay, so that's going to be an important caveat that sometimes people miss. So now this is done, and I have everything saved in history, right? Whatever this history is, all of this training process is saved in there, right? So now I can take advantage of it. So let's break this down. Exactly what is history, right? Let's just plot it. Well, so first of all, it's a function, right? So basically, what I'm doing here is every line and every letter in this code is now saved in history. So it's not strictly an array or a vector of these numbers, right? I need to extract it. So fortunately, there's this thing called a dot history. And if you can't remember dot history, all you gotta do is you put a dot here, and then something will pop up. And then whenever you see I don't know what you call it, kind of like a range, a tool symbol. This means that this function belongs to that object. So whatever this callback object is, if you put a dot, and then the epoch, history, model, these three functions on top, they all belong to that object. So you can click on epoch, there's something out, right? Something come out. And then, or you can click dot, and then click on history, something will come out, right? Now I have something to work with. I know that these are numbers, and then I can start from there. So one thing that's important is this is actually called a dictionary. Dictionary is a special data type. So how do I know the dictionary? Well, first thing you know is this bracket. But if you can't remember that, all you gotta do is you do a type function and you throw whatever you want to check inside of this type function. And then you run it, it will tell you DICD, that means it's a dictionary. Okay. But since you already know, then you can just run it, it will give you this. So dictionary means what? Dictionary is kind of like a hash function, right? There's a key and there's a value. So key are basically referring to these names that are in the strings in the beginning. So you can do bracket, quotation mark, loss. It will give you this first vector here under loss. Okay, so you run that, that's going to be here. Or you can say val loss, that's going to give you the second one. All right. If you don't really know what are the keys in the dictionary, then you can either just run it. It will tell you loss or val loss, or I believe there's a function called keys. Maybe I'm lying. Oh, it is. Here. So sorry, parentheses. There we go. So this way, it will give you the actual keys of this dictionary, right? Because what if you have 100 epoch, right? Then that table is going to be like super long, and you're going to have to scroll down to see all the names. Well, that's not going to happen, right? No one's going to scroll on 100 lines. So you do without keys, it will tell you each and every name in that dictionary. And then you can just save it somewhere or memorize it. And then you say, oh, loss. Boom, that's all numbers. So that's going to be how you extract the result out of the whatever model that you train, right? Now we need to plot it. So we grab that and we say dot plot. And something happens, right? So this is called a line plot. And how I know a line plot is here. It's a line plot. It means it's a line. It doesn't mean it's continuous. It's not, right? It's 10 numbers. How can it be continuous? It's quick. It's just line plot draws those lines for you. It's a style of plot. It doesn't mean that there's something in the middle that's 0.5 epoch, right? That's not a thing. The computer draws this line for us, okay? So that's something that just to be aware of. But here you have loss and you have val loss. So what that means is you have two losses, right? And the reason you have two losses is because the first loss is coming from your training data, and the second loss is coming from this validation data. So if you want to plot something, you better plot two plots, okay? So how do you do that? Well, you can do things a little bit differently. I'm going to show you the most easier way. So easier way is plt.plot, and you plot the second plot. So history dot history bracket val loss. This will give you two lines. And then you just make it a little bit prettier, right? You say plt.title. You can call it whatever you want. You can say path for loss, parentheses, training, and val, so validate. And then you can do a plt.show, and then it will give you a plot with the title and with two lines, okay? You can even do a legend. So plt.legend, and then parentheses, and then make sure that you have this bracket. If you don't have this bracket, it won't recognize what legend are you doing. So you have to be a bracket. Inside a bracket, then you can tell the computer, this is a training, this is testing. But make sure you tell the computer training and testing the same order as the plot. If this is a training and this is testing, you write the training first. So you say training, testing, or validating, right? Because if you flip the order, then obviously the color is going to get messed up. So you run that, that will give you the plot. You can, of course, give a different size, plt.figure, and you have to specify fig size equals to, and this is going to be a parenthesis, okay? And in the parenthesis, you can specify whatever width and height of the plot that you desire. So you can say 10 by 10. So kind of look like that, right? That's 10 by 10. But if you feel like it's too big, then you can make it smaller, right? You can say 6 by 3. Of course, it'll be smaller. right? So this is one way to go. Another way to go is you plot two plots, right? So if you want to plot two plots, you have to specify which subplot that you are plotting, all right? So you can say plt.subplot 1, 2, 1. So this means number of row, number of column, and which plot it is. So same with the second one, you say plt.subplot 1, 2, 2. Okay. But then notice that if you do this way, this title and this legend will only work with the second plot. And you enter two strings in the legend, so that's not going to work. The computer is not going to recognize what this is, right? So you need to get rid of this, and then you need to specify in the title. You say, hey, here it's a validation, so VAL, and here is the training, so plt.title train. This way, the computer will register which one is which. But of course, you probably want to make it wider because this is two plots. So you can see two plots. But since each plot only has one line, then obviously just one color. You won't have two colors. So that's kind of the whole situation here. And you can kind of, from here, you can kind of make a judgment call, right? You say, oh, this is a good model. I'm good with it. Next step. Or you can say, hey, this model is a good start, but I feel like we can get this better. That's fine. Then you can keep going. So how that works is you come back up and you can say, hey, well, this model is just one layer, right? Why don't we make it a little bit more layers? So how you do that is you can set this as a latent, I don't want to call latent, I want to call hidden layer. So you can design hidden layer. And then you're going to have to finish with output layer. Output layer always have to be 1. Okay? So this always has to be 1. In the beginning, you're always going to have an input shape in the very beginning. So maybe I should say this is the first layer. And then maybe in the middle, you can have hidden layer. And then for hidden layer, you can do a linear model add, and you can add whatever you want. tf.characters.layers.dense, dense, and then you can enter a number, let's say 128, comma. And then from here, you have a couple of choices. You can do activation function. You can specify as ReLU. And then people might ask, what is ReLU? ReLU is a type of activation function, and it takes the following form. So maybe you say ReLU is max x and 0. Let's give an input x. Okay, so what this means is, it means that we compare x with 0. If it's positive, we let it go. If it's negative, we replace it with 0. Okay, so that's what's happening. So why do we do things this way? The reason we do things this way is because in this data set, and again, this is in this data set, it's not an overall generalization, right? It's in this data set. In this data set, we are talking about housing value. Housing value cannot have negative number, right? I'm buying a house, no one's paying me, right? I'm paying somebody else. So that's why it's it cannot be a negative number, even though linear regression gives you negative numbers. Does that make sense? So we say that we recall linear regression model can give us negative values, but this data we predict housing price, and it cannot be negative, right? That's the reason here. So in other words, in other words, you might say, well, this is kind of case by case based, right? It is case by case based, right? We don't know to do this until we see the data. If you don't tell me what data it is, and you're like, oh yeah, which activation function should I use? I have no idea. I need to see what the data is. Okay, so this is again, it's a choice by a data scientist based on observation of the data. Okay, so this I really want to emphasize because people ask me questions about this before, and people are very confused why to make this choice. This is why. Okay, so that being said, these two numbers are completely up to you. You can do 1 to 8, completely up to you. You can change this to 64, completely up to you, right? Now you have a new model. Of course, you rebuild the model, so you run that, and you of course have to recompile, and then you can retrain, and then you wait a little bit, and then you print out the results. So I'm gonna save this plot here, and I'm gonna try to generate a new one just to have some comparison. I'm not so sure if there's a big comparison because this is only 10 epoch, right? You can kind of see that the first model starts from 0.1, and the second model starts from 0.03. So immediately it's already started to pick up things, right? If you want to have a fair comparison, maybe you need to change the y lim. So let me see if I can do that. Which plot is this? Let's see, PLT y lim. Yeah, and I think I need to specify 0 and what number is this? 0.1. Sure. So I'll say 0.11. Something like this. Now you can kind of see the comparison, right? What is the comparison? The comparison is if I give a couple of more hidden layers in the middle, not a couple of more, just really just 2 more, right? So let's write a note here. Path for loss. This is 2 hidden layers, right? Where this is 1, but I can't really run this again because I don't have the memory, right? This history now it's now overwritten by this one, right? So if I run this code, I'm going to lose the graph. So I'm not going to run this code, but notice that this is coming from linear regression model where this has 2 hidden layers. And so what's the difference? Well, this is the difference. Can you still tell which one is good, which one is bad? Well, not really from the end because they both flatten out and they flatten out. So not so much to compare there, but you might be able to say that the model with a couple more hidden layers might have a small edge in the beginning of the training. And the reason I say that is because I look at the error and the one with hidden layer, it starts with what? 0.04, that's the error. Whereas if you don't have the hidden layer, if you just have a linear regression model, it will start you off with a 0.1, or here it's about 0.07, which is a lot higher than 0.04. Does that kind of make sense? So that is the difference here of sometimes, why people prefer to go with neural network. Any questions so far? Yeah, don't hesitate to ask me questions. I feel like a lot of you guys maybe people are a little bit shy. Sometimes people ask me great questions in the chat. So yeah, so keep those up. I really appreciate it if someone asks some questions once in a while. Just make sure that what I'm talking and people have a good reflection. So yeah, let's take a quick break because it's about an hour, so it's a 5:50 at my clock. So I'm gonna take a quick 10-minute break. I'm gonna come back around 6 o'clock. So take a break, and I'll see you guys in 10. Okay, so when you generate a model, right, you need to save the output somewhere. So if I don't have this, then whatever I'm training will not be stored in this object here. Now, that being said, this object is your choice. You don't have to call it history. You can call it whatever you want. So
here, I'll show you. Let's say I run this build model, and then I compile, and then I fit. Let's say, let's make it a little bit less confusing, right? Let's say this is whatever you train. Okay, let's make it less confusing. So you do your usual training job, and it's going to run the loop, run the algorithm, it's going to train it, right? And once this finished training, all of the parameters that's trained, the best parameters, well, best in terms of 10 epoch, right? The best parameters, the log, the val log, all that results will be saved in this object that you define here, right? Called whatever you train. So I'm going to grab this, and I'm going to come down here. I open up a new code block, and I print it here. I run it. Now notice that this says what? This says keras callback history. So basically, it is essentially a function that saves all of your code or all of your model and output and everything that's coming out of this .fit. Now it's saved in here. So that's what the first history is talking about. Now there's a second history, right? The second history is always called history. It's not whatever you want. It's always called history. So you say dot, and then it will pop out this window, and there's epoch, there's history, there's model, right? What you want is the history. This is the actual history of your training path. You have logs, you have val logs. That is the actual numbers. So what you do is you say dot history. The first name, you can call it whatever you want. The second name must be history. Because if you don't write history, the computer doesn't know what you're referring to, okay? So now this history, you can run it. It will give you this thing that has a bracket, and then a log, column, a vector, and then another val log, column, vector, right? So whatever this is called a dictionary. So if you don't know the data type dictionary is essentially a JSON file, kind of like a bracket. So I can say bracket, and then maybe I say A is 1, B is 2. So this thing by itself is a dictionary. A dictionary is referring to this type of data type that has a name and has a value. Now, the value doesn't have to be numbers, right? It can be another letter or whatever you want, right? It can be, let's see, apple. That's fine, right? So you can define this as a sum dictionary, and then you can print that out, and it'll give you this curly bracket, right? So it's exactly the same thing here. If you want to run that, it'll give you a curly bracket, a name, and then some numbers. Name, some numbers, and then close curly bracket, right? So that's what the dictionary means. So now you understand the data type is a dictionary, right? Then what you're going to do is you're going to take these two numbers and you're going to plot it. So what do I mean by that? You have a dictionary and you know the key, right? This is the A, this is the B. So how do I get this 2 out of this dictionary? Well, you just call B, right? Because that's the key. So you say sum dictionary bracket, and then you say B. It will give you number 2. And it's just as simple as that. And as a matter of fact, you can have more than one number. You can say bracket 1, 2, 3, 4, 5. And you can run that. Now, this 1, 2, 3, 4, 5 will be stored according to this key called B. Key is just a name. It's like the second entry, the name is B. It's a vector, 1, 2, 3, 4, 5. It's as simple as that. So you call B, now it'll give you 1, 2, 3, 4, 5. Right? Now that's going to be your data, right? Then you can plot it. So then you can throw this entire thing in a plc.plot function. Now, of course, it will just give you a line. And the reason is because this is a plot function. You can maybe use if you want to use scatter plot, then you need to plot the other dimensions. I'm not going to do that. But here, let's say just plot, I'll give you 1, 2, 3, 4, 5, something like that. Except that, start with 0. So that's why it's 0, 1, 2, 3, 4. There's not going to be 5. So that's kind of what's happening. And does that kind of answer your question? I know somebody had a question about dictionary. Any more questions about dictionary or about the history?
I have a question.
All right. So, yeah.
It's not about the dictionary or history thing. It's about the, like, when you're adding the hidden layers, what are those layers exactly doing? Like, how does that change the result?
Oh, that's a good question. So let me show you. I wasn't going to tell you guys on two neural networks lecture, but since you asked, I'm going to tell you. So what's happening here is this. Let's say I have one layer, right? Let's break this down. One layer model. So what this doing is, and again, I'm going to use latex, okay? So bear with me. So I'm going to do a bracket. So I'm going to do a B matrix. And then let's say you have a couple of neurons, right? X1, X2, X3. But let's say that's pretty much what I have. And then you have an arrow, and then you're trying to produce some sort of output. If I just give you one output Y, then it's simple, right? Then you know that this arrow in the middle is really a vector. It's a vector of W1, W2, W3. Okay, and this way you will be able to essentially produce this Y here, right? So this is a one-layer model. You can kind of think of it as a linear regression model. So think of it as linear regression model. All right, so that's one layer. Now, your question is, what happens when you add more hidden layers? So let's talk about that. I'm going to cheat a little bit. I'm going to grab this code, and I'm just going to type again. So this is a multi-layer model. So this, you can essentially call it a neural network. Call it a neural network. All right, so I'm going to put the code here. So what's happening is this. Not only do we have these three features, X1, X2, X3, generate one output, we have this generate a couple of outputs together, and we're stacking them, okay? So bear with me, I'm going to draw it in front of you guys. So instead of going to Y directly, we are going to go here first. So let me just complete the graph, right arrow, and then here, instead of calling it X, I'm going to call it A. So A1, A2, A3 are three neurons for the hidden layer 1. So this, I'm going to call it hidden layer 1. Except that I'm going to put it in the text, otherwise I can't see the spaces. There we go, hidden layer 1. So now this way, the X1, X2, X3 is going to map to each one of these A1, A2, A3 first, okay? And I said each. So what does each mean? Each means this. If you have W1, W2, W3, then you're going to map to A1. So you need to really make sure that this W1, W2, W3 has a has kind of like a sub-index. So let me add a couple of brackets. Right. So let's say W1, W2, W3 are pointing to A1. So what you need to do is you need to say comma 1. And same with W2, comma 1, and W3, comma 1. So now these three take care of A1, right? So let's draw it out. What does that look like? So what that looks like is this. Where's my pen? Here's my pen. This is X1, X2, and then you have a X3. And then you have A1, that's a neuron, right? Let's draw a circle, that's your neuron. This is A1. And then the first model is this. That's one line, that's another line, and then that's another line. And these W1, 2, 3 pointing to these three arrows. But it's for A1, right? It's the first neuron. That's why we add comma 1, comma 1, comma 1 here. So now you might say, okay, what happened to A2 and A3? Well, you got to keep drawing. So let's draw another circle. Here is another circle. And then you have A2. So I'm talking about the second one, A2, right? Second one. So you got to draw each line, right? So that's one line. That's another line. and then that's another line. And when you draw that line, you're going to realize that, okay, wait a second. These three lines are not exactly the same as these three red lines, right? The purple lines and the red lines are, two different things, right? So then what's going to happen is you need to add in W1, W2, W3, but now this is for the second neuron. So then you need a comma 2, and a comma 2, and a comma 2, right? So now, with that being said, I can erase all these graphs, because once you guys have the visualization, I can now show you what it looks like in a math diagram. Okay, so I'm kind of running out of space here, but I'm going to try my best. So you're going to have W1, comma 2, W2, comma 2, and W3, comma 2. Right, that's what you need. And the first three W's is for A1. The second three W's is for A2. Okay. Now I'm gonna maybe put them in a bracket so people don't get confused. Is that a bracket? Oh, come on. Like this. Okay, that'll give you a bracket. And the same thing with all the comma 2's. So I'm gonna take that and then give me a bracket. There you go. And then obviously you do the same thing for 3, right? So I'll just cheat. I'll say vector W3. But this way you can cheat it, okay? So does that kind of make sense? So this is what we call a forward propagation. A forward propagation is referring to the information flow coming inside of your features, which is your X. That's your input layer. And then it goes to this network architecture and sent to the hidden layer, and then it goes out. And of course, when it goes out, you need to have 3 more parameters, right? So let me draw this here. So let me switch a different color. Let's say this is A1, you have A2, and then you have A3, and then this is your Y, right? So you gotta make one line here, and one line here, and another line here, and then you have new parameters, right? So whatever W is called now is not going to be these W's, right? It's not, right? It's new W's. So you call it whatever you want, right? You call W1. Here, I want to avoid all these things, right? So I'm going to say comma L. W2, comma L. This means the last layer. So W3, comma L. Does that make sense? So this way, you notice that these 3 W's are completely different animals from all these W's in the beginning. Right, they are all trainable parameters. Okay, so now you kind of get the idea. The fact that I am doing this and I'm doing this is essentially just adding more information in a model. So this 128 means what? 128 means I'm doing this. So this is 1, and this is 128. And then 64 means what? Okay, so 64 means I'm doing 64, right? So obviously it's a slightly narrower, right? That's 1, and that's 64. And that's so on and so forth, right? So you gotta connect all the lines. Like this, and then the same thing here, right? And so on and so forth here. But here you're predicting one number, right? Just housing value. You're not doing classification. So you just have one neuron in the end, and that's Y. And then you're done. Does that kind of answer your question? Good?
Yeah, I think that helps.
Yeah. Yeah, that's a good question. Don't worry about it. We're gonna come back to this at least 3 more times. Okay, so don't worry about it. All right. So that's what's happening when you're doing these hidden layers. Now, that being said, people might get confused. What's the benefit of doing this? Well, based on what we've seen so far in computer vision, as well as in some other applications such as NLP, we typically find that the deeper the architecture is, the better the performance. Now that's a big if, okay? It's not a causation, okay? I'm not saying that deeper will absolutely have to give you a better performance. Right? That's not what I'm saying. I'm saying if your model is well trained and all the other factors are held the same, the chances are deeper the model, you have a higher chance of getting higher performance. That kind of sounds like a mouthful, but it is indeed what it's supposed to be. So I just want everyone to know that it's not always the case that the deeper the better, right? It's always the case that it depends on data, okay? So you're gonna have to try it, right? So what I would recommend is this. Since we had, like we know all these plots, we know all these results are coming out, and we know how to essentially run through these entire experiments, right? So what I would recommend is, let me just get rid of some of these junk. I'm gonna comment that out so it doesn't bother me. Same with this one, so it doesn't bother us. All right, so I'll leave it in the I'll comment it out so it's not deleted, right? You can still refer to the code if you're confused, but I'm not gonna try to run it. So here's what I would recommend. What you're supposed to do is you have two models. So I'm going to copy paste, put it here. This you call a model 1. And then this you call a model 2. And the model 1, maybe you just do one layer, right? So you get rid of that, and then this is just 1. So this is just a simple linear regression model. There's no hidden layer, there's no neurons, nothing like that, right? The input coming in, one set of weight, done, prediction. So this is the second model, obviously 2 layers, right, in the middle, and then maybe a little bit more complicated, right? So what you're supposed to do is this. There's one more thing that I think is beneficial. It's going to be what's called a model evaluate. Okay, so this is going to be evaluation. So what does that mean? When you train a model, let's say here, what do you have? You have where's the model? Linear model. So let's grab that, and then let's put it here, linear model. If you put a dot here, you're going to realize that this is a function called a predict. This predict is essentially basically the same as what we talked about before, right? The model, model fit, model.predict, all those things are exactly coming from the same template, right? It's cut from the same cloth. So what that means is you can use this predict function and throw in the test data. And this is essentially how you evaluate your performance. So what we're going to do is I'm going to show you 2 ways. Where's my test data? Here. So X test and Y test, right? So this entire way, we haven't touched X test. We haven't touched Y test. The model doesn't know what they are. So that's a complete fair comparison. If I use the model, perform on that, and I get some accuracy or I get some error, that error is honest, okay? You can kind of take it for granted that tomorrow somebody gives a new data set, then whatever that error is going to be similar as this test error, all right? So we're going to work with this X test. We're going to work with this Y test. So there's a couple of ways. The first way is you do, let me skip this first. So the first way is do a model.evaluate. You can throw in X test and Y test. You run it, it will of course give you some sort of value, right? 0.01. 0.01 is your loss, or it can be whatever you define here. If you define this as something else, then it's something else. But here, I define MSE. So this number is MSE, okay? So let me put a note here. This gives you whatever you define in model.compile, right? You run again, it gives you that number, right? But it's the exact same number. It should not be a different number. So this is the one way that you can check it. So of course, you got to write it down, right? You say, okay, conclusion. All right, I'm going to draw a table. Table in Markdown is like this. Let's say you have a model, and then you have this is a score, right? And then maybe you have some other MAE, let's call it different function. And then you need to draw a line. So this will give you a separation. And then you can draw your model. Let's say it's a linear model, linear. And then the score is exactly what this number is, right? So you just take this number, and then you copy it down here. Boom. And then you got to work this out, and then you got to work out a 2-layer model, right? This is a linear model. So now this way you have a comparison, right? You know exactly what language are we talking about. Is it good? Is it bad? What are we talking about? Right? This is exactly what we're talking about, right? Score 0.01. Is it good? Is it bad? I don't know, right? I gotta run the rest of the experiment. So I do that, and then this is one way to evaluate. So we're gonna say evaluation 1, and then obviously you can do a different way, right? Evaluation 2, and then you say linear model predict. This is to use predictions. Use predictions. So essentially, you're doing from scratch. You're not using the evaluation function, which will do it for you, right? You do it from scratch. You say predict X test. This is obviously going to give you some sort of prediction, right? So this is the prediction on test. So now you're going to have to do something with it, right? Chances are you're going to have to compare this with Y test. And we said that here we want MAE, right? MAE is like this. You either do from scratch or you use some scikit-learn library, right? And I'll show you both. So the easy way is obviously you say scikit-learn metrics MAE, and it should be able to give you the mean absolute error. This is the API of that particular library, okay? So the easiest way, right? The easiest way is you copy this and then you come back here, you import the library, you say library MAE, you import it. And then obviously once you import it, you just run it, right? So you run it like this, copy that, and then you come back here, you say, paste it here, and then the Y true is obviously gonna be Y, what do we define? Y test. And then Y predict is gonna be this thing, right? Prediction on test. So this way, obviously it gives you some sort of performance. But this is use the library, right? But if you want, you can do it from scratch by hand. So you say you take that number, subtract X, not X, sorry, Y test. You need to give a parenthesis. This will give you a vector, right? Oh, sorry, what happened? Oh, a data array problem. All right, let's check that out. So it's a dimension problem, right? So what is the shape? The shape is by 1. Okay, so I'm guessing this is not by 1 then. So let's check this out. Comma, star, shape. Okay, so 1 is by 1, 1 is not by 1, right? That's where the problem is. So we gotta reshape this. So reshape, and then if you put a minus sign here, you should be able to flatten it. And then you can check it out. Aha, now it's flattened. So you can use that and then put this in here. Now you'll be able to compute their difference. So let's try it. Okay, so that's the difference. But this is the MAE, right? The mean absolute error, right? What does mean absolute error? Let's try it. Mean absolute error is this. Mean absolute error is, you can say MAE given Y and Y hat, that's the ground truth and your prediction, is what? Is your, obviously divided by sample size, right? And then you gotta add all the differences together. And then inside you have absolute value of Y minus Y hat. I should write the subscript because it indicates how many sample you have. This way, you have your mean absolute error. That's the formula, right? So we take this prediction, we subtract this Y test, that's your ground truth. Order doesn't really matter because A minus B is A minus A, is absolute value is the same. So you do MP dot absolute value, ABS. This will give you all the absolute value, right? So this is equivalent as basically what's happening inside of the summation, the sigma symbol here. So then all I gotta do is add them together, right? You can add them together divided by n, or you can just take the mean. So I'm just gonna take the mean because that's a faster way, right? And you should be pretty much exactly the same as this number, right? Except that here we're doing this calculation by hand, and here we're using the scikit-learn library, right? They should be exactly the same. All right, so this is gonna be a draft. And this number is essentially what we need. So we grab that number, and then we put it here. MAE, right? We're gonna write something here, I write something here. All right, so that's where we are right now, right? So we say we fit a linear model. Did I actually fit a linear model? Okay, let's retry it, because I feel like I didn't do that. So I'm gonna comment this one out. I'm gonna run this, right? Linear model. And then I'm gonna compile, and then I'm gonna do .fit. And I grab this result. And I have to wait for this to finish training. But once it's training, I just need to grab this, whatever you train. And then I can essentially skip all these plots. And I come down here, I put it here. I'll plot it because history is changed. So let's plot that. Yeah. And then this linear model, that's the same model, right? Because here we use the linear model, okay? So once we have that, we can come back, we can do evaluate. Okay, so it is a different number. So let me grab that. And then let me put it here. So it's no longer 0.01, it's 0.02. And then I do the same thing with the MAE, right? Mean absolute error. Now give me 0.10. So it's about it's about 0.1. So I put that here. All right. So that's my linear model. And then I gotta do the same thing, the exact same thing with a different model, right? So I come back up here, I say, okay, let me comment this out. And then let me run this, right? So I put my cursor here, I run this, and I gotta recompile, and I gotta retrain it, okay? Now this way, I have a new model, right? Now this linear model is completely different from the previous one, right? Same with this memory here, completely different from before. And now I plot it, obviously it's gonna be a different plot, right? Slightly different. And then I do my model evaluate. Of course, it's gonna give me a different number, right? This one. So I grab that, I put it here. Okay, let's continue. I make a prediction and I do my mean absolute error. Now it's this one, right? Okay, now we're talking, right? Now I have a story to tell. I did a linear model, no hidden layer, no whatever, right? Just a linear model. I connect all the lines and I make a prediction. The score, which is mean square error, is 0.02. That means the MAE is 0.1. But if I add two layers, the score is 0.016 and MAE is 0.09. Every other factor is the same, okay? The only thing different is the layers. This linear model has no hidden layers. The two-layer model has two hidden layers in the middle. So obviously the two hidden layers is doing something, right? They're learning something that the linear model can't, okay? So this is one small demonstration of why people prefer deeper model. And we haven't even trained anything. We only did 10 epoch, right? In reality, you can do 50 epoch, 100 epoch. Chances are you're probably gonna see a bigger difference. Okay, so then you can go to your presentation. You say, okay, let me copy this table down to my presentation. That's gonna be a good story to tell, because you have a new model, it's doing better, right? So this is a kind of like a general template of how you make new discoveries, like why this model is better. You gotta show with results on test set why it's better. Okay, let's take a pause. Any questions? Somebody asked a question, what values do X and Y tests hold? X and Y test. Oh, you mean the X test and Y test? So the X test is the data in the test set. So specifically, it's the features. So it's these guys. Obviously, without the housing value, right? Because that's what we're trying to predict. So Y test is the housing value. So median housing value. So it's the exact same thing that we want to predict, but from a different set of data. Does that kind of answer the question? And somebody said, why do we use hidden layers? Oh yeah, so the hidden layers is this. You won't know to use hidden layers before you see this result. You won't know that. So that's a good question. If you just show me the data and you're like, oh yeah, I'm coding the model. How many layers do I use? I have no idea. I don't know that. I only know it after you try it and after you see this result. Then you can tell a story. Okay, so you won't know it. So sometimes like sometimes you see people do this, like they have some sort of overall big hypothesis that they're trying to throw at people, and sometimes they're like getting empty and they actually said it before they run the experiment. That's usually a very dangerous game that you're playing. You know, typically what you want to do is you want to just sit back and relax a little bit and run a couple of models. And once you have evidence, you come back and say, oh, okay, the 2 layers is better. Do I know the 2 layers is better before I see this? Absolutely not. I don't. So that's a good question. Why do we use hidden layers? I have a hunch that 2 layers is better in this case, not because I know the future, but because I've done similar things in the past. That's how I know. And what is the next question? Could you give me an example from real life that you use? In real life, I think in terms of maybe when I'm doing publication or write a paper, I will almost always go just a couple more layers, see what the model can do, right? Let's say I have a hypothesis. Let's say I do my research and I'm trying to figure out what paper I'm trying to write, right? And then it turned out, based on my research, somebody said, oh yeah, 3 layer is absolutely the best one. You can't beat it. Usually when you read the paper, somebody will make like a bold claim like that, right? And then I will read that claim and I'll try to figure out a code and I'll try to duplicate their results. And 2 things can happen. After I try to figure out what they're doing, either I believe that's true or I don't, right? So if I believe that's true, then fine, I'll let it go. Nothing happens. Because there's no research opportunity, right? You know, if I agree with you, there's no novelty, right? We're on the same page. Nothing new happens. But if I disagree with you, right? You say, hey, 3 layers is the best, and I work out the code, maybe I show 5 layers is the best, then I have a shot of a new paper or a new idea. Then the story continues, right? It doesn't mean that we hate each other. It just means that the disagreement now is giving birth to a new idea. So usually if that's the case, and oftentimes that's the case in writing papers or publications, you find yourself in that situation. So when that happens, then you do exactly what I just said. So you're like, okay, somebody said this is the best. Well, let me go a couple more layers. Let me see what I can do. And if you can do better, then you can beat that performance, then you have a shot. You have a new idea. Then you have a discovery, right? So I don't know if you mean like real life. If that's what you mean, I'm not sure, because usually this is inside of either academic environment or like at my job, people do similar things. But at my job, no one's trying to beat somebody else. You know, as long as solve a problem, then you're good to go, right? Unless somebody is making a bold claim saying whatever model they develop is absolutely the best, which no one does, and no one says that in the industry. No one has a guts to say that in the industry. You know, then there's no back and forth going on. I don't really have to, you know, beat your model, right? Typically, people will come up with in industry, people will automatically generate this table. No questions asked. That no one is saying the first one is better, second one is worse, or no one is saying the first one is the best. No one is saying the second one is the best either. Usually in industry, people generate table automatically, right? And you know, whatever model you pick, I mean, you pick from the table, right? You don't have to debate with me. You don't have to argue with me. So in the industry, people do things a little bit differently because everyone has the same goal, right? To get the job done. Get the job done, you get paid, you go home, right? In academically, it's slightly more different. Maybe you have more debates, maybe you have slightly more arguments, and and also academically, people are trying to make a name for themselves. They publish papers, and that usually leads to some bold claims or bold conclusions. And usually when that happens, you have a shot of essentially taking their models down, and it's essentially basically introduce your own model. And exactly how you do it is pretty much what I said. You do theirs, and then you do yours, and then you show that this new idea, which is deeper layers, will give you a better result. Does that make sense? Cool. Yeah, so that's kind of like a long answer for a short question, but I think it's okay. So now you guys get the sense, right? So what have we talked about? We have talked about linear regression model, and we tried two models, right? One is linear regression, one is two hidden layers, right? So now we're going to do the same thing, and we're going to review this code again, but with a different data set, right? So what we're going to do is we're going to introduce this new data set that I feel like I probably talked about it before, but that's okay. I'm going to repeat again. So I'm going to introduce this new data set called MNIST data set. Oh, maybe I haven't talked about it before. Yeah, let's talk about it. So now we're going to be in this is a regression. Now we can go to classification, so that you guys can do both, right? You can do both. All right, so classification. First thing is to load the actual data. So we use Tensorflow API to load the data. So it's called tf.keras.datasets.mnist. Oh, by the way, if you do dot and you just stop, right? You wait a little bit. You actually have all these data sets, and you can actually use whatever you want. Each different data set is doing different things. So obviously, you're not going to be using the same model. What we're going to introduce here is a classification problem. So we're going to use MNIST because that's a classification data set. So typically people in a classroom environment, usually the data is a little bit more selected. Now, of course, in real world, that's not how things work, right? But in this case, I want to show you guys how classification problem works. So obviously, you're going to have to pick classification data, right? The function is called load data. And this will essentially download all the data, and you're going to have to save it somewhere, right? So the first thing you do is training images. I'll just say X train, Y train, just simply because it's faster. X train, Y train, and X test, Y test. So notice that if I start running this code, I will overwrite whatever memory of X train, Y train I saved before, okay? Because Python, the memory continues, right? If I don't do anything, I just start running this code, of course, these things will get overwritten, okay? So really make sure that if you're developing multiple different models in the same script, this is what you have to pay attention to, right? In this case, I want to focus on this one, so I don't really care if I lose the memory from before, so that's fine with me because it's in a classroom environment. But for you guys, in your own data set, if you have a different model or different data set, you better make sure that these names are unique, okay? So I'll leave that to you guys. All right, so we download the data, obviously wait for a little bit, right? Download data, and then you give a sanity check. So display dimension. All right, let's see, xtrain.shape, ytrain.shape, xtest.shape, ytest.shape. So this tells me the dimension of the data. And then you're like, wait a second, what are these things? Well, these are picture data, right? Obviously, I'm not expecting you guys to know that. I'm telling you right now. So this is actually a picture data. And these are width and height, okay? So how do we evaluate this? Well, you can plot it out, right? So we have this PLT library that we loaded up, right? This is a library. And we can just plot it. So we say plot. And then obviously you can plot the picture, .im show, that's the function for you to plot the picture. And parentheses. So now this is where the argument goes, right? That's the input of the function. You either give a two-dimensional array or a three-dimensional array, but the last layer must be size of 3. That's it. You cannot put in anything else. So let's talk about that. Argument 1. The first type of argument input is a 2-dimensional array, 2D array. The second one is a 3D array, but the last dimension has to be 3. Okay? So you take the first one. How do you do that? You say x train bracket 0. It's going to be like whatever this is, right? I can't really see what that is. It's just a bunch of numbers in an array, right? So I do a dot shape, just give myself a sanity check. Oh, okay, it's a matrix that's 28 by 28. So that's fine. So it's 2D array, right? That's 1, that's 2 dimensions. So I just throw that inside of the initial function, and it'll work, right? It'll give me a picture. So this is actually a grayscale picture. So this probably won't make too much sense because it's not grayscale, right? I need to force it to be grayscale. So you do color map, C map equals to quotation mark binary, and this will give you a grayscale. Okay, and then you can maybe do things a little bit differently. You can say, let me grab that. Let's say for I in range, let's say 25, and then you obviously give a subplot. 25 is 5 by 5. Right? So the 5 rows, 5 columns, and this is I plus 1, because I plus 1 is indicating which plot it is. And unfortunately, it has to start with 1. So that's why we do I plus 1. Of course, in the initial function, there's no longer 0, right? Otherwise, you'll be plotting the same graph. So you do I. And then I believe that's probably about it. And then you can just say plt.show. Then it will give you a grid of plots that's like 5 by 5. So there. You can make it slightly bigger if you want to. We talk about the PLT function figure, right? Fixed size. Of course, you can make it bigger. 20 by 20, of course, it'll be bigger. Right, like that. So yeah, I'll make it smaller just because I want to see everything. So quick classic. All right. So this kind of gives you an idea, right? That's what data look like. It's pictures, 28 by 28. All that sounds clear, right? The job is simple. Your job is to build a model such that it can predict all 10 classes. Okay. So how do I know there's 10 classes? Well, you have to check it. So you say y train, and then you can do an np.unique, and you put it here. All right. So this gives you 10 classes, and then you can count it, right? You can count the length. LEN, that means length. You throw that in there, I give you 10. So this 10 means what? This 10 means whatever neural network model that you're building, the last layer must be 10. It must. It has to. Otherwise, something's going to go wrong. Okay. So you can copy from the code above, but of course, I'm not going to be lazy. I'm going to try to do it in front of you guys. So this is going to be a build model, right? And it's the same thing, right? You're going to have 2 of these things because one model is deeper, one model is narrower. So you say model equals to tf.keras dot and model and sequential. And then you can do your usual drill, right? This is input. So model.add tf.keras dot model. Wait, dot layers, I believe. Layers. Thanks. The first number, you do whatever you want. But notice that there's an input, right? The input shape must be the shape of the data. If your data is 20 by 28, then you better give 28 by 28. Otherwise, something's gonna go wrong, okay? So here you say 28 by 28. Oops, 28. And then there's also this thing called the activation function. Now, this is where activation function will be helpful in the middle, right? So why is it helpful? Think about it. You are predicting what? You're predicting per class the probability that this picture is one of those 10 classes. Like, give me a picture, let's say this one. You have to tell me probability that this picture is number 1. Digit 0. And then probability the picture is digit 1. Probability the picture is digit 2, and 3, and 4, and 5, and so on and so forth, right? So think about what that's going to do to your model. Do I care about negative values? I don't, right? I'm trying to classify something so that the output is a probability. So I don't really care about negative values, okay? So which basically means what? Which basically means I need ReLU in the middle. Does that make sense? So that's what's happening here. And ReLU kills off the negative values, right? Because we talk about up here. Bear with me, let me find it. Here. So it compares whatever x you give me with 0. If x is positive, I let it go. Nothing happens. If x is negative, I replace that x with 0. Okay? So in other words, I don't really care about negative values. And you shouldn't care because you're trying to predict the probability. There's no negative 5%, right? It's not a thing. So you do that. And then I'll leave that to you guys, whatever you guys want to do. I'll make it a logistic regression first. So this is just a output. And then hold on, this might not be able to work because this might not be able to, because this is you can't connect this. So let me flatten it. So model.add ts layers dot flatten. Yeah, there we go. Flatten it. And then if you flatten it, then you don't need a 28 by 28. And then last layer, you need a softmax. And when we build deeper layers, we're going to use ReLU. All right, so flatten, and then this is output. So in other words, I'm trying to force this to be a logistic regression model, but for 10 classes. Okay, so hopefully that runs. All right, it works. Now I'm going to do the same thing with compile. You always need to compile. Model.compile. You have loss. That's going to be MSE, and your optimizer, that's going to be SGD, stochastic gradient descent. As you run that, and obviously model.fit. Now, I'm not going to tell you guys why, but I don't think this works out well. So let's try it. X train, Y train. All right, so X train, Y train. Let's say epoch equals to 10, and then let's say validation split is 20%. Right. Obviously save as history, right? So history. All right, let's see. Yeah, this error is blowing up. So I don't think this is performing well. So I'm gonna add a metric such as accuracy. So this way we know what we're talking about. I did not do accuracy for the previous model because previous model is a regression problem. The accuracy cannot be defined. Okay, it won't make any sense. So in this case, I'm gonna add metric equals to accuracy, and then I'm gonna try again to see how this works. And then I'll show you guys real fast after this. All right, bear with me. I'll just stop it. I'm pretty sure it's not gonna work. Okay, so I'll run that, and then I'll run that, and then I'll run that. See, now here's the problem, right? What happened here is if you look at the accuracy, it's like 0.09. And that's going to be a big problem, right? Because think about it. You have what? 10 classes. There are 10 classes. Like we saw in the beginning, using the unique function, right? Here, the unique function, there are 10 classes. 0, 1, 2, 3, all the way to 9, 10 classes. So think about it. If I randomly draw a class, I get what? 10%, right? If you randomly draw one, it's as if I'm learning nothing. If I'm not learning anything, I'm randomly draw, I'm holding my eyes blind, I'm randomly draw one. What do I get? 10%, right? 10% for each class. So in other words, this is what? This model didn't learn anything, right? It didn't learn anything. It's about 10%. At 0.099, that's 10%. Okay. So let's leave it here. It's kind of like a cliffhanger, but let's leave it here. Take a break. In 10 minutes, we'll come back. We're gonna pick up from here, and we're gonna check out why it's 10%. So take a break. I'll see you guys in 10. So let me really make sure that this is understood. So what's happening is this: we train the model, right? This is our data, and then we plot it, and we have some sort of visualization, so we know that this is what we're working with, and we build a very simple model. It's not supposed to work well, so we build a very simple model, and we train it. It turned out it's just about 10% of accuracy, so it's not supposed to be well. It's not a good model. So when we do the model.evaluate, the model.evaluate is going to evaluate your data on the test set because we fed in the test set data. But the model is defined using the loss here and the metrics here, right? So, whatever these two numbers are, it has to be linked towards these two evaluation metrics defined in your compiler. So in other words, the first is actually your loss, and the second one is actually your accuracy. So you can kind of say that, okay, this is about 11.6. So we're talking about 12%-ish, not even. So that's kind of how good it is, which is really not that good, okay? So we're going to take our template, right? We developed this template. Let's grab that. And then you can come down here. Let's write some notes down. You say conclusion. This now is a logistic model. Of course, it's a 10 class. So you write 10 class, and it's not doing a great job, right? How do I know that? Well, we have two things here that need to be changed. First thing is loss. Second thing is accuracy. And then you put the loss in there. What is that? That's 27.25. And what is your accuracy? Your accuracy is about 116, right? And these things we're going to have to update later, right? Because we have a new model later on. So whatever this is, it's, we'll just leave it like that. All right. So this is where we are so far, right? We tried logistics, didn't work, right? So now we're going to try a different model. So we're going to come back up here, and we're going to say, where's our model? Here's a model, right? This is a model one, and then we're going to do a model two. So now this doesn't work anymore, so I'll just comment that out. Now we're going to put a new code block here. We're going to put this thing here. Now we're going to develop a new model. So let's try it. We have flattened, so let's leave like that. And what we said was to add a hidden layer, right? So let's see, hidden. And then we have model dot add ef dot chars dot layers dot sense. And then I'm doing 128. And then the activation function, I can say rating. Let me make sure I'm on the right track of, because I feel like somewhere I need to specify a dimension, but I have not yet done that. Yeah, I don't think you need to. It's weird. Yeah, okay. So flatten. Once you flatten it, it doesn't really matter because it's flattened anyway. So you have 128, and then that's your hidden layer. And then here maybe you have. Let's make a couple more. Right? Model dot add tf dot chars dot layers dot dense. Let's say 64. And then same thing, activation equals to rating. And then let's make one more layer, like that. And then let's make this 32. Let's see. Okay, let's try that. And then there are more things that we can try, but let's see if this works. Either it works or it doesn't, but we won't know until we run it. Oh, I had a typo here, my bad. Keras. Keras. Same with this, K-E-R-A-S. All right, so that's our model. Compile, make sure we compile correctly, and then model.fit. So run that, let's see. Oh man, still not that accurate. Layers pattern. You're also going down a little bit. That's interesting. Let's see. What are some other things I can do to make this better? So, oh, I know what I'm calling is. Okay. So here's what I did wrong. I did not do one hot info. I actually missed that part. So let me make sure this is clear for everyone. It's actually good that I do this myself live as well, so I can remember myself. Okay, so this is Y train, and this Y hat. Let's just run Y train first. As you see, it's a vector of numbers, right? So a vector of numbers, it is not one hot encoded. And here's the problem. If it's not one hot encoded, then it is not towards a certain class. So in this case, the computer is going to think of this 5 as a numerical value 5. So if there's a 1 somewhere, then the 5 is 5 times that 1. That's not going to be correct, right? So what we're going to do is use this function called a two-categorical. So we're going to say Tensorflow.keras.utilities function, utils, and this is two-categorical. And then you throw your Y train in there. Now it's not going to be a big vector, it's going to be a matrix. Okay, and I'll explain to you guys what this means. So this is the one hot info. And let me use my favorite language, LaTeX, to type out what's happening. So I'm going to design a bracket matrix, and then I'll walk you through what I mean. Let's say I have a vector, right? It's a vector. Let's just take this. What do we have? We have Y train. So whatever this is, right? Let's say 504, right? Let's make it simple. So 504, right? That's the bracket. That's the vector, right? Let's keep things simple, right? Let's just take the first 3 numbers. So one hot encode. What does that mean? This is going to be one hot. All right. What does that mean? What that means is you're going to take each level and turn that into a binary column. Okay. So I'll repeat that again. So you take each level, right? So the first level is, we're going to do this line by line. So I want to make sure everybody's clear on this. The first one is 5. The second one is 0. Third one is 4. Okay. I want to make sure it's a bracket. So like this. All right. So 504. First level 5. Second level 0. Third level is 4. 5 doesn't mean 5 times whatever. Right? There's no numerical value. It's a class. It's a digit 5. It's a class. So we're going to check this column and create a matrix that's only ones and zeros by checking if they equal to this particular level in the original vector. So we're going to check one by one. Okay. First one is going to be here. Let's write it down. What do we have? 5, 0, and 4. Right. That's going to be my vector. So the first one is we check with 5. Is the first one 5? Yes, it is. So we say 1. Is the second one 5? No, it's not. Right? So we say 0. Is the third one 5? No, it's not. We say 0. All right, done. Now we go to the second column, 0. Is the first one 0? No, because we're 5. Right? So this is a 0. Is the second one 0? Yes. So we say it's 1. Is the third one 0? No, right? It's 4. So this is 0. And then now you guys get the idea, right? Now we check 4. And then it's going to give you what? 0, 0, 1. right? So now you're done. This is called the one-hot encode. It takes each level, check with the original vector. If it's the same, you register as 1. If not, you register as 0. And now you have ones and zeros only. And it's going to be a new matrix. Okay? So with that being said, now let's write it down. This is going to give us, so 5, that's going to be 1, 0, 0, right? And the second column is going to be 0, so that's 0, 1, 0, 0, and that's 1, and this is, oops, my bad, and this is 0. All right, we're almost there. The last column is going to be level 4. Level 4 is going to be 0, 0, 1. So this is 0, 0, 1. So this action is called a one-hot encode. And after you do it, you will have everything in a new matrix that's either ones or zeros. So once you do this, you're going to have a new Y train, right? So we're going to say Y train one hot. And you're going to do the same thing with Y test, right? So Y test Y hot equals to tf dot errors dot util dot to categorical. And just throw in Y test in there. So after you do this way, you can do a quick sanity check, right? Y train one hot dot shape, Y test one hot dot shape, and it's by 10. Why is by 10? Well, because there are 10 unique numbers, right? So this way, you should be able to get a much higher performance, because now you have each level to be binary. It's as if you're running a probability model for each class. So with that being said, now we can run this, and then we can run compile, and then we can run history. Hopefully it goes up. I'm not sure. Let's see. It's something else, I think. Oh, my bad. It's not Y train. Sorry, it's Y train one hot. Right. Oh, come on. It should be going up higher than that. Oh, there we go. Okay. Now it's learning. All right. So, well, that took a lot of detour, but we finally get to where we are, and now the final accuracy is picking up. Now we can run our analysis. So 10 epoch, it's not a whole lot of epoch, right? So it's learning something. Obviously, if you want this to converge, you're gonna have to wait a little bit longer. But in a classroom environment, let's try to save some time. So I'll just stop at 10 epoch. Whatever it does, we're gonna pretend that's the best it does. So now at 10, it's trying to wrap things up, and now it's done, right? So you do your X test, make sure on the Y test, you're doing one hot, right? I forgot that like twice. So hopefully this will serve as a memory purpose. You can check it, it's about 84%, 85%. So let's write that down. This is about, your log is 0.028, and then your accuracy is about 0.85, so it's about 85%, 84%, 85%. So the first thing, we need to redo that, right? Because we messed it up earlier. So what I'm gonna do is I'm gonna comment this out, and then I'm gonna redo this just to give a fair comparison. So again, no hidden layer, right? You come in, you flatten it, you generate your 10 classes, and that's it. So we run that, and then we're now running this, right? Because we wanna have a comparison. We run that, we recompile, and then we're gonna retrain and make sure there's a one hot encode version, not the original version, right? So now let's train this, and then let's see how accurate this is. Hopefully it's higher than 10%, right? So hopefully it's learning something. But the question here is, can it beat 85%? Right, that's the question. We're gonna wait a little bit, see how this goes. But after I do this, I'm gonna wait a little bit, give you guys 10 to 15 minutes of time, and then you guys gonna train this model yourself. And then I'm gonna ask you guys, bring you guys back in about 10, 15 minutes of time. I'm gonna see who performed the highest. Okay, so what I'm talking about is this number here. If you can get higher than 85%, please let me know. Okay, so here we're gonna say student model, whatever that is, and whatever that is. All right, so we're gonna wait and see what it does, right? So it's about 10 epochs, and this is about 83%. But that's a validation set, right? So let's see what the evaluation on the test set does. So you run that with a little bit, it's about 83.6, so that's about 84%. So let me write that down. So that is about 83.6, so 837, and this is not 27 because we messed up earlier. It's about 0.0324. All right. So now we have a comparison. Okay. And then I can tell a story. I say, hey, logistic model is doing somewhat okay-ish. It learned a little bit about something. The accuracy is 83%. But if you do a two-layer hidden layer in the middle, you're able to increase to 85%. Right? That's the story we're trying to tell. That's the comparison. And if you can get something like that, that's going to be a good table to put in your presentation slide. Okay? So this is now saved in the folder called class notebooks, and it's the notes for July 21st, 2022 notebook. So everyone is supposed to open it, and please make sure you save as a copy in your own Google Drive, so that hopefully I can preserve this and don't overwrite my results. I'm going to give you guys 15 minutes, run your own model, and feel free to change whatever you want. Okay, we'll talk about a couple of things to change. Please change whatever you want. And then you can just start from here and then run through the entire thing all the way to here, and you check out what is the final accuracy. And again, it's on test set, right? The test set accuracy, not the training set. Training set is going to be higher, right? So it's a test set accuracy. And then in 15 minutes, I'm going to ask you guys, and then everyone's going to type their answer down to the chat, and we're going to see a flush of answers, and we're going to see which one is the highest. All right. So let's run this experiment and go ahead and get it started. And then I'm going to count 15 minutes, and then I'm going to ask you guys again. So you don't have to drop out or anything. You can just do it in front of the camera. So try it. And these are the areas that you can change. This number is the width of the network. Change to whatever you want, right? You don't like 128, change to 200, change to 300, change to 1,000 if you want to, right? Same with these lines, right? You don't really have to have 3 dense layers, right? No one says that's the best one. You can have 5 one, you can have 10 of them, you can have 20 of them, right? You do whatever you want, right? So let your imagination fly, right? Follow your imagination, do whatever you want. And then, try a couple more times, and then we're gonna check this number. And I'm gonna look at my clock to count 15 minutes. I'm probably gonna create a poll just so I'm not like sitting here staring at the screen. All right. Don't let me bother you, okay? I'm gonna try to create this poll. Okay, so what is your accuracy on the test set? So this is a test set accuracy. what's happening is this. So in this exercise, there are a couple of things that you can change, right? The beginning, not so much, because you do have to flatten it. Otherwise, you can't connect. And in the end, not so much, right? Because there are 10 classes and you have 10 neurons. So nothing to change there either. But in the middle, you feel free to do whatever you want, right? So I wrote here about the width and about the depth. The width is regards to the number. Specifically, these numbers that you see, they're called units, or sometimes they're called neurons. I should probably put a note here. So these are units or neurons. So the bigger these numbers are, the wider that dense layer is. And that's the width. And you probably won't be able to say width of the entire network, but you should be able to say width of each layer. Because the entire network can have different layers. So width, then you run into a problem of, well, which layer are we talking about? So when people say width, usually we're talking about a particular layer. Then you're gonna have to specify how deep the model is, or in other words, how many dense layers you have. So in this case, the width is, you can essentially summarize your entire model into a list of vectors. You say 128, 54, and 32. Then people know, oh, you have 3 hidden layers. First one, the width is 128, second one 54, third one 32. So then this way it's clear. So what I would recommend you guys to do is take this number and you run through the entire thing, which we just did, right? And then you put it here. So you say this is like that. You put it like that. And then you can do another model, right? You can say, hey, 128 is probably not that good. Let me change a different number. Let's say 1024, right? And then this way, you change this number. So it's a different model. If it's a different model, then you're gonna have to run everything again, right? So then you go back up, you say, okay, what if this is 1024, right? Then I have to run this, boom, and then run compile, boom, and then run history. So you run that, and then now it's gonna trying to train and then trying to learn this data with the new model. And then you wait a little bit, you kind of already get a sense that this is a little bit slower, right? The reason this is a little bit slower is because, well, you have more parameters, right? You have more units of neurons that you need to train. So of course, then it's slower. That's kind of how things work. And somebody asked a great question about Epoch. Epoch is also another thing that you can change. Here in a classroom environment, I actually didn't really play a whole lot with this. But if you want to, you can specify in your conclusion. You can say, hey, this is, you can add a new column, right? You can say Epoch. And then you can just add a couple more bars, and it will give you a new column. And the logistic, I think here we try 10, right? So you say 10. That's going to give you number Epoch. Here we also try 10. And then here we also try 10. So in other words, all these are 10 epochs, right? It's okay if you want to try more epochs. You're going to have to make sure that you document it correctly. So you can have the same model, and then maybe you can try 100 epochs, right? Then who knows? Maybe this is going to be a different number. Then this is going to be a different number. Hopefully, the accuracy goes up. And it should be, right? Because you're training more epochs. So that's kind of what's happening here. Now you see that I have trained this just 10 epochs, nothing else has changed. So whatever this performance increase I'm having must be coming from that small tweak of a model that I just did, right? Because without that, I didn't change anything else. All the other factors are exactly the same. So then I can write it down, right? I can say, hey, this is 1024, this is 54, this is 32, this is 10. I did not change that at all. So then what's going to happen is I can say, okay, let me run my evaluate. And then maybe I get a different model, right? The different model is in here, in this case, is slightly better, 0.020. And then the accuracy is 0.885. So this way, I know that, okay, So now we have a story, right? Everything else is the same. The only thing that's been changing is 128. I just changed 128 to 1024, which is like almost 10 times bigger, and now it's a better model. How do I know it's better? The loss is smaller and accuracy is higher, right? 88% is higher than 85%, and the 0.02 is less than 0.028, right? So the errors are smaller, the accuracy is higher, and only 10 epochs, nothing else being changed, okay? So now somebody asked me, okay, what if you change more epochs? Yeah, that's fine, you can do that. So you're just gonna have to change this back, right? Because otherwise, how do you know where the contribution is coming from, right? So you're gonna have to change this number back, and you run this code again, and we recompile, and you do mod.fit. Sorry, I did not do 100. Let's try 50, because I worry this might be a little bit slow. So I run that, I recompile, and then I do mod.fit. And now this is 50 epochs, okay? So obviously it's gonna take a little while, right? And then as this is training, I'm gonna keep talking about what's coming up next. So the next step in the pipeline is this. After today, you guys are gonna go back and you guys are gonna play around with your model, play around with the data set, and you're gonna be like, oh my gosh, this is so slow. Every time I do something, I have to wait for forever, right? And there are ways around that. And we're gonna talk about all of that. But one famous thing is you productionize your entire pipeline and you write these installable functions, okay? So these functions you can pack together and you can write it as an installable library and post it on GitHub that people can download and people can run directly, right? You don't have to rewrite all these lines of code every time you open up a new data science project, right? That's crazy, right? So the next step from today, I'm not sure if we have time because it's already 7:50. So the next step from today is to essentially introduce you guys that entire pipeline so that tomorrow when you guys, finish, essentially the first week of the program, you're gonna know a little bit about linear regression, a little bit about logistic regression. And from today, we talk a whole lot about coding and TensorFlow, of which we build a regression problem, we also build a classification problem. So hopefully you guys have a different variety of models ready in your, in your toolkit, such that when you go kind of build your own model, you're kind of like, you're not like complete blind, right? You have some sort of strategy ready to go. So I want to get you guys set up here, and please make sure you talk to people and tell us what is your team based on whatever you tell, whatever results that you communicate with people. From last session, we allow students to be with their own team. So basically what that means is they're a team by themselves. So one-person team, you can do that if you want to, although we recommend you to be in a team, but it really is not necessary. Some of these data science projects, you could very well take care of it in a few days of time, especially the source code are all provided to you guys, right? You guys don't really have to magically invent all of this, right? The code is here. As I said in the beginning of the program, I really encourage you guys to copy code from internet. Please do that, right? This is not a TED talk, right? This is absolutely, please copy code from internet. Don't reproduce code, right? You learn from a source first. You identify a pain spot, and then you reproduce a new code. Without that, don't just automatically start reproducing a new code, because you're going to get yourself into a dead end, and turn out that end of the day somebody else is doing a better job, and it's already there, right? Einstein has done it, Newton has done it. There's no reason you guys shouldn't do it. So please do that. Copy code from internet. And then I believe we're done. This is pretty high already. It's 93%. So Epoch definitely helps, right? So let's run this last thing. Just make sure we're on the same page. But hopefully it's about 93%, which it is. Now you can write it down and have a comparison. You can say, hey, this is 0.01. This is 93, so 0.93. Boom. Now you have a comparison. Okay, you have a two-way comparison, not just a comparison, you have a two-way comparison. First of all, no hidden layer and there's hidden layers, right? So you can even expand your table like this. You can say hidden, use hidden, right? And then here you say no. For the everything else, you say yes. Same with this, yes. And same with here, yes. And the last one, yes. So now you have a comparison, right? Oops, I think I made a mistake somewhere. Oh, sorry, that's the. So the first one is a no, my bad. Okay. Now it's clear, right? So first model, no hidden layer. We have our input, we flatten it, we send it into output, predicted, right? 10 classes, done. And I know it's a not very good model, even though it's already at 83%, right? So it's learning something. It's not learning nothing, right? Earlier, we had a mistake, right? So let's write that down. So the mistake is we did a logistic model, but we do not have one hot encode, right? So no one hot. So it's as if you're not really doing a 10 class, right? Each level is kind of has its own numerical value because you did not separate different classes, right? You're not doing one hot encode. So we did 10. Unfortunately, the error is large, right? 27. And then this is about 10%, right? So it's pretty bad. So now you can kind of see the difference, right? That's a bad model, not gonna work, right? 10% is like random guessing. Let me make sure this is correct spelling. All right, second model, maybe it's learning something, 83%, so okay, maybe it's learning something, but it's not that high of a performance. And you don't know this is not gonna be a high performance until you run through the rest of the model. So you have to be willing to try new models before you know if this is good or bad. When we are here, when we are in a second model, we do not have the rest of the model. We don't know if it's going to be a good model or bad model. We can only compare with 10%, which is nothing, right? So, so this is going to be a crucial point for you guys. How do I know to run this? Well, technically speaking, I don't. I have a hunch. I don't necessarily know to run this. So that's kind of like the punchline here, which is you're going to have to run through a variety of different models with different designs, and you better write the formula down, right? You better write these things down so that you can make a fair comparison. And what's a fair comparison? Well, if you're going to increase epoch, then make sure you don't change anything else. Because if you increase epoch and you change something else, then how do I know the performance increase is coming from the epoch or coming from something else, right? So make sure when you change something, just change one of them and hold every other factor constant. And then you have a fair comparison. If this is 85% from the beginning, and then you change to 100 epoch and it becomes 93%, then we have a shot, right? Then you can say, okay, the story is the increase comes from the number of epoch. And that's how you build up your data science project, which is to run through different experiments and kind of get a sense of more like a trend or like a direction of how to change your model such that the accuracy is higher. All right, so I think that's pretty good for today. We're gonna leave the rest of the material for tomorrow. This code is here, so you guys feel free to take a look at this code. I'm gonna write out a small recap to summarize what happened today. And by tomorrow evening, please make sure you have a team set up. Either you're by yourself or you're with your teammates. If you don't say anything, we're gonna pretend that you don't have a preference. Then what that means is we're gonna put you in a random team, okay? Unless you tell us otherwise. And Sam and I will work together. For those of you who don't really have a preference, we're gonna pretend that you're indifferent. So we're gonna put you in a random team. But if you do have a teammate or if you do prefer by yourself, please let us know. All right, so that's it for today. 2-3 minutes early, but that's okay. I think this is pretty good so far. And this code is online. So if you want, you can check it out and run through some of your own experiments and then see what you get from there. And tomorrow when we come back, I'm gonna talk about a little bit about the logistics of the project and talk about what you can do and what kind of data sets can you find, and so on and so forth. So yeah, that's it for today. And I'll maybe say a few more minutes for questions, but I do have to go at 8 o'clock, so not a whole lot of time. But yeah. Oh, by the way, sorry, I keep forgetting. Let me send you guys a survey. Yeah, thank you. Really appreciate it if you guys can fill out a survey. And then, yeah, feel free to drop off. Yeah. Yeah, bye, Sam. See you guys tomorrow.